So today we are doing section 3-4. It's linear programming, and our learning objective is to solve problems using linear programming. Essentially what we're going to do is we're going to graph a set of inequalities and find where all their regions cross and get a region that is a total solution. So not just having two inequalities cross, we're going to have a bunch of inequalities cross. So the definition of linear programming, so make sure you guys are writing this down. Linear programming is a method for finding a minimum or maximum value of some quantity given a set of constraints. And a constraint would be like, we want the number of people on our field trip to be less than or equal to 20. Or we need to make at least $100 in order to achieve our goal. All right, so once we figure out our constraints, they're going to create a feasible region. And a feasible region contains all the points that satisfy all the constraints. And so what I want you guys to do is sketch this feasible region here. It's got 4 constraints. The constraints together make a nice little trapezoid. This trapezoid, where our constraints overlap, is called our feasible region. All right, one more little snippet of information for you guys to write down. The quantity you are trying to maximize or minimize is modeled with an objective function. So there's going to be, we're going to take our feasible region. We're going to look at what lives inside or makes up our feasible region, and we're going to put that in and find what maximizes or minimizes our objective function. So like profit or population. All right, so if it says take note and it says it's a key concept, we must write it down. So the Vertex Principle of linear programming, and just to remind you, each little corner is a vertex. So the Vertex Principle of linear programming says if there is a max or a min value of the linear objective function, it occurs at one or more vertices of the feasible region. So once I find my feasible region, I'm going to write down my vertices, and I'm going to plug that x and y into our objective function. You can solve a problem using linear programming by testing in the objective function all of the vertices of the feasible region. Okay, so we're going to write down these constraints, and right now we're just doing the basic problem. So this is the basic problem without any contextual information. So we're just thrown some linear constraints, and we're asked to, our objective function is p equals x plus 3y. What values of x and y maximize p? So the first thing we're going to do is we're going to graph each of these constraints. And I prefer to have everything in y equals. So I am going to solve each one of these guys for y. So I have y is less than or equal to negative 1/2 x plus 2.5. Second one So I'm going to subtract x from both sides. And then divide everything by -1. And when you divide by a negative, your inequality switches. And -x divided by -1 is x, and 2 divided by -1 is -2. All right, so let's do some graphing. So let's graph our first one, and we'll actually red and blue. So we start at 2.5. Here's our x and our y. Make sure you guys are getting your graph paper out, because this would be, when you're doing linear programming, if you're not on graph paper, you are really going to struggle to find the vertices, because there's a precision in the graphing. So I'm going to start at 2.5, which if I'm counting by ones, is right here in between 2 and 3. And then I'm going to go down 1 over 2. And follow that same pattern backwards. And then we definitely get out our straight edge so we can make our straight line. Check in, I am a solid line because I am equal to. And I want to shade everything below. So let me get the highlighter out. Actually, I'm going to do crayon. All right, so let's graph this green line, this green guy here. Inequality. He's going to start at -2, and his slope is up 1 over 1. And I'm going to follow that same pattern all the way across my graph, only because it takes mere seconds to draw a dot on the graph. All right, let's get out our line. We, of course, want to make a straight line. So I'll make it, then I'll move it so it's lined up. And I am greater than or equal to, so I'm going to have a solid line. And I want to shade everything above. So I'll go ahead and get out my green crayon. And shade everything above. So where the two overlap is right around this little triangle there. Don't forget, I have 2 more constraints to add in. So I'm going to have x greater than or equal to 0. So that is this vertical line here. And that's all this. And then I have y greater than or equal to 0. So that's my x-axis right here. And I want everything above. Okay. And then I'm going to go and take my pen or my pencil, and I am going to really darken in the desired area. So that would be So we look, yellow. So it would be that quadrilateral right there. Well, I'm in the middle of lecture, so I might as well. Now we need to pick out our vertices. So if we look right here, one of our vertices is going to be at 0, 2.5. So I'm going to list my vertices over here. It's the y-intercept of my blue line. I'm going to have another one here at 0, 0. While 0, 0 is not going to probably ever maximize our function, it definitely might minimize our objective function. We have another one right here, and that's where this guy, that's at 2, 0. It's where our green line hits the y, or the x-axis. And then our last one is here. Where our blue line and our green line intersect. So this point looks like it is at 3, 1. And because my graph is a little cray-cray right there, we're going to go ahead and plug in 3, 1 and see if we get where our lines cross. So when I plug in 3, do I get equivalent statements? Half of 3 is 1.5. So negative 1.5 plus 2.5, is that equal to 1? Yeah. All right, so confirmed. The last coordinate is at 3, 1. So now I need to, I'm going to erase this real quick. So now I need to take a look at my objective function. And I want to maximize it. So I'm going to plug in 0 for x and 2.5 for y. Then I'm going to plug in 0 for x and 0 for y. Then I'm going to plug in 2 for x and 0 for y. Then I'm going to plug in 3 for x and 1 for y. And we're going to see which one of these gives us max. Is this 7.5? 3 times 7.5. This gives us 0. This gives us 2. And this gives us 3 plus 3. So which one of these maximizes our function? So 0, 2.5 maximizes our objective function. Okay, so we're going to take a look at the t-shirt scenario. We are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival. And we have to work within the following constraints. So go ahead and write these constraints down. You have at most 20 hours to make the shirts. We want to spend no more than $600 on supplies, and we want to have at least 50 items to sell. The other information that may be a little bit difficult to read, it takes 10 minutes to make a one-color t-shirt. I don't know. Supplies for the t-shirt are $4. And profit is $6. For a 3-color sweatshirt, it takes 30 minutes to make. The supplies cost $20. And our profit is $20. Okay, take a moment and write all that information down. Lesson 0. Okay, so let's fill out this little chart together. We're going to just put together all of our information, the number of minutes, the amount of each one, the cost, and the profit. Okay, so for my t-shirts, we're going to let X equals our t-shirts. So the number of minutes it's going to take to make X amount of shirts is going to be 10X. So with 10X, how long is it going to take us to make our sweatshirts? So it was 10X, and it's going to be you're going to make me pause the video like this. Times the, so it's 30Y. So it's the amount of minutes it takes to make one times however many were put together. So our total is going to be the sum of these two. So it's going to be 10X plus 30Y. So now we're looking at the number. How many t-shirts are we going to produce? X of them. And how many sweatshirts does that mean we're going to produce? Y. And our total is going to be oh, hold on. I need some room over here. Sorry, buddy. Okay, so our total has to be in minutes. We have to relate it to the 20 hours. How many minutes is 20 hours? There are 60 minutes in each hour. So that would be 1,200. So we know we definitely have to be less than or equal to 1,200 total minutes. Huh, say that again? Well, what's the it's going to be defined by our constraints. So the number of t-shirts and the number of sweatshirts has to be at least 50 items. So we want that to be bigger than or equal to 50. So our cost, it costs $4 to make a t-shirt times however many t-shirts we make, and it costs $20 to make a sweatshirt times however many sweatshirts we produce. We want to spend no more than $600 on supplies, so our total, 4x plus 20y, has to be less than or equal to 600. So we want to spend no more than $600 on supplies. So the cost of our t-shirts plus the cost of our sweatshirts has to be smaller than or equal to 600. And then profit. Profit-wise, we make $6 for every t-shirt, and we make $20 for every sweatshirt. So the total is going to be 6x plus 20y equals our profit. All right, so given this information, let's put together our constraints. You guys want to do the easy ones or the hard ones first? The hard ones first? Okay. So the first constraint is the minutes. So 10x plus 30y has to be less than or equal to 1200. And then our other constraint is the amount we have to sell. And that is x plus y greater than or equal to 50, because we want to sell at least 50 of them. And then the last constraint is the cost. And 4x plus 20y less than or equal to 600. The profit, this is your objective function. And that will be the function we'll be putting our vertices into. So we're putting him off to the side for just a moment. The easy constraints. So the easy ones are, am I going to ever have negative amount of t-shirts? No. So my x value is always going to be greater than or equal to 0. Am I ever going to have a negative amount of sweatshirts? No. So my y values are always going to be greater than or equal to 0. So this is linear programming has 3 steps, 3 easy steps. The first step is going to be to graph the constraints to form the feasible region. So because I cannot be below the x-axis or below the x-axis or to the left of the y-axis, we know everything above the x-axis is going to be in our feasible region, and everything to the right of our y-axis is going to be in our feasible region. And well, I'll go in and show that in a second. So the next thing we have to do is solve these equations for y so we can graph them. The other alternative is to put in the intercepts and graph based on intercepts. Yeah. Okay, so what we're going to do is we're going to graph these. Now, if you want to solve them for y and graph the y-intercepts and the slopes, that's fine. And that's definitely a good method. I'm going to show you the intercepts method. And before I do that, I'm going to first simplify our inequalities. So this first inequality, 10x plus 30y less than or equal to 1200. I'm going to divide everything by 10, and it's going to bump everything down by a factor of 10. So 10x divided by 10 is x, 30y divided by 10 is 3y, and 1200 divided by 10 is 120. Then I'm going to use, I'm going to plug in 0 for x and get 3y less than or equal to 120, divide by 3. I'm just going to change this to an equal sign because I want that coordinate. 120 divided by 3 is 40. I put 0 in for x.
Oh.
So my first coordinate here is 0, 40. And let's go ahead and count by tens. So blue line has a dot at 0, 40. And then I'm going to plug in 0 for y and find my x-intercept. So we get 10x plus 0 equals equals 120. Wait, I bumped it down. X plus 0 equals 120. So when y is equal to 0, x is equal to 120. So let me find that. 70, 80, 90, 120. So it's right here. So now that I have the intercepts, I'm going to draw a line.
How do you get 0?
I selected 0. So when you're finding a y-intercept, you plug in 0 for x. And when you're finding an x-intercept, you plug in 0 for y. So one of them is going to bump down to 0. So the other coordinate is 120, 0. And that's how you use intercepts. You don't have to use intercepts. You can use the good old slope-intercept form. Totally fine. I just thought I'd show you guys one more time. Okay, so we need blue line, and he is going to go from here to here. And he is solid. And then I want all my y's less than this line, so let's shade below. Okay, so I'll show you the intercept. We'll go back to our slope-intercept form for this guy. So I'm going to subtract x from both sides of this equation. So I get y greater than or equal to negative x plus 50. Which means my starting point is on 50. And my slope is down 1 over 1, negative 1 over 1. But I'm counting by 10, so I'm going to go down down 10 over 10. So I have that nice little green line. I can equal, so I'm going to have a solid green line there. And then I want everything above that green line. So get my green crayon out. And I'm going to shade everything above. I'm going to go ahead and not shade above the blue line because I know my constraint says can't go above that blue line. So instead of confusing myself with extra shading, I'm just gonna go ahead and keep that there. And then remember our constraints. X has to be greater than 0, so I can't go anywhere in this zone over here. And Y has to be greater than 0, so I cannot go below the x-axis. So my feasible region is this little triangle right here. Okay. Hold on a second. I gotta modify because my little blue line is not at the right angle. So you can see he needs to go down. Allow. There we go. So in actuality, it's this vertice right here. Which is why precision graphing is mega important. Okay, so we are going to graph. So we graphed the constraints to form our feasible region. We're going to find the coordinates of each vertex. So I'm going to take the easy ones first. My first one is at 50, 0. This one is at 60, 70, 80, 90, 130, 110, 120. 120, 0. And then I have this one here. I think he is somewhere like 10, 35. But we are going to double check just to find him for sure. All right, we forgot to graph one. This guy. Sickles. Okay. So we're going to subtract 4x from both sides. And divide by 20. Negative 1/5 x plus 30. Ooh, I like him. Okay. So this guy has a starting point at 30, and he goes down 1 over 5 or down 10 over 50. Okay. Let's throw Mr. Red Line on there. Ooh, I like him even more. Okay, so we are going to shade everything below that. Because here's our y, and he's less than or equal to. So get our shading out. Okay, so I'm going to draw on here where our feasible region is. So it is here, here, here. So it's a nice, funky little quadrilateral shape. So with that third constraint, not counting the x greater than and y greater than 0, we still have the vertices at 50, 0 and at 120, 0. We now have this vertice here, which is where these two lines intersect. And we have this vertice right here, which is where this line and the green line So blue, this is where blue and, so we're going to have to find where our first constraint and our third constraint intersect and where our second one and our third one intersect. So let's get some work. All right, so I have this guy y equals negative x plus 50. I have, I'm going to rewrite this in y equals form. So he is divided by 30. So he is y equals negative 1/3 x plus 40. And then my last one is y equals negative 1/5 x plus 30. So I want to find where these two lines cross. I want to find where this line and this line intersect and where this line and this line intersect. So the algebra behind our vertices is we want to see where negative x plus 50, this line right here, this green line, is equal to our red line that we drew, which is this one here, which is negative 1/5 x plus 30. So I'm going to add an x to both sides, and I get 50 equals 4/5 x plus 30, because negative 1/5 x plus 5/5 x is 4/5 x. Subtract 30. I get 20 equals 4/5 x. I'm going to multiply both sides by the reciprocal. Divided by 4 is 5, and 5 times 5 is 25. So this coordinate in our feasible region is 25, comma. Then we plug that back in. If I plug it into here, if x is equal to 25, 25 plus what has to equal 50? 25 plus what has to equal 50? 25. So our vertice here is 25, 25. We are now just missing this one here. And he is where that red line, which is negative 1/5 x plus 30, and the blue, nope, and the blue line is this one here. So I need to find, I need more room. I'm running out of room. So I need to find when 1/3 x, oh, we're so almost done. So I need to find when 1/3 x plus 40 is equal to my, so that's this blue line, is equal to this red line here, which is our 1/5 x plus 30. So I'm going to add 1/5 to both sides. Now let's add 1/3 to both sides. 1/3 x I get 40 equals negative 1/5. So that would be 3/15 plus 1/3, which is 5/15. Gives us 2/15 x plus 30. I'm going to subtract 30 from both sides, and we get 2/15 x equals 10. We're going to multiply by the reciprocal. Divided by 2 is 5, and 15 times 5, 75. So x is equal to 75. We're going to take that and plug it back into, let's plug it into here. So negative 1/5 times 75, well, 75 divided by 5 is 15, we just did that. And negative 15 plus 30 is 15. Okay, so now that we have all the vertices, we're going to evaluate P. So our profit, remember we put it on the table, we're like push it away, 20x, or 6x plus 20y. So we're going to plug in 50 for x and 0 for y. We're going to plug in 120 for x and 0 for y. We're going to plug in 25 for x and 25 for y. And then we're going to plug in 75 for x and 15 for y. Let's go ahead and do those calculations together. 6 times 50 is 300. 6 times 120 is 720. So far, he's the winner. 6 times 25 is 150 plus 20 times 25 is 650. 6 times 75 is 450. And 20 times 15 is 300. And 450 plus 300 is 750. Oh, he wins. So because this guy is the biggest, x equals 75 and y equals 15 maximizes our profits. So we need, sorry, I'll bring that. So we need to sell 75 t-shirts and 15 sweatshirts.